Welcome back, everyone. We'll now begin with the afternoon session with an invited talk. I would request Dr. Kamarika Bhattacharya ji to please come and chair the session.
Thank you. So our last invited talk is by Professor N. Raja on computer-aided theorem proving. He is well known to us, and he has always been a big supporter of CAI from the beginning. And whenever we wanted to talk to him, invite him, or do ask for some indulgence, he has always been uh, kind of uh, allowed us to do that. So, Professor N. Natarajan is, Professor Raja Natarajan is a faculty member at the School of Technology and Computer Science, TIFR Mumbai. He specializes in models of concurrent and interacting processes, logic and foundations of mathematics, automated and interactive theorem proving, programming paradigms, and formal methods in computations. He has served as an editor for Logica Universalis, Sadhana, and has co-edited volumes in distributed computing and internet technology. And he is a prominent figure in the interconnections of mathematics, logic, and computer science. So today we are going to have a great talk from him on computer-aided theorem proving. So over to you, sir.
So, good afternoon once again. And before I begin this talk, I have some disclaimers. First of all, there is nothing with CA with cellular automata in this talk. Yeah? So, if you're going to be disappointed, then this is the time to be disappointed. Yeah? And secondly, there is going to be nothing original in this talk. Yeah? If there is anything original at all, it's going to be by mistake. This is more of a survey of an area. Two of my PhD students have written a thesis in results in this area recently. I don't want to speak about that, but let me get too specialized. Instead, I thought I would give a overview of this area so that people in who are already working in CA may find some connections, may find some interest in this. You know, either way, either by applying CA to this or using this for work in CA. So with those disclaimers, let me begin. This is going to be the outline of my talk. I give some historical introduction, and then I talk about theorem provers and computer algebra systems. So you remember the title of the talk, it's computer-aided theorem proving. So there have been distinct communities, research communities in computer science, which have tried to use computers to prove theorems. And they've gone their own separate ways. And there are two major communities among them. There are those who do work with computer algebra systems, and then there are those who work on theorem provers. Yeah? So I'll give you some highlights of this kind of work, of these two branches. Then I'll tell you a little bit about research in automated reasoning, and we look at a couple of applications of automated reasoning. Yeah? And so one of them is in computer science. There are several applications. I'll show you two major ones. One of them is to do with proving correctness of software and hardware, and the other is to look at proofs in mathematics and foundations of mathematics. and then we'll conclude the talk. So here is the, so here's the beginning. So what we are trying to do is we are trying to do proofs with computers. So the idea of, so you want to reason and you want to reduce reasoning to some kind of mechanical calculation. Yeah, this idea is not new. It's been around for several centuries. This is Thomas Hobbes, who was a famous philosopher. He made this analogy explicit. He said, reason is nothing but reckoning. Reckoning as in calculation. He said reasoning is just calculation, nothing more. So this was developed by Leibniz, who envisaged two different things. One, universal language, yeah, what he called the characteristica universalis, in which to state your problems, and then a calculus of reasoning, a calculus ratiocinator, with which you could solve those problems. And so Leibniz's dream was very grand. So he said, if there are two people who have disputes, they come to a court of law, and to resolve it, the judge writes down their problem in some formal language, and then in the language that he called characteristica universalis, and then do some calculations, and then the disputes will get resolved. You know, this was the kind of dream he had. Of course, this is completely unfulfilled. Yeah. So he made some steps towards coming up with this language and doing some things about this kind of reasoning. But his work was very lofty, but it's all largely forgotten, his work. Yeah. So, I mean, you can see this is too grand a dream. It remains unrealized, and possibly maybe it's completely unrealizable, the kind of thing that Leibniz had in mind. But, and then, but at least something has happened in a more specialized area, at least for mathematics. Over the last few centuries, a kind of language has been developed that's adequate for most of mathematics. Yeah? So we cannot resolve human disputes with this language, but at least we can try to solve problems and theorems in mathematics. And the first really successful symbolism was developed by George Boole, and this was quite successful for set theoretic and logical reasoning. And not just that, Boole was the first one to emphasize the possibility of using some formal methods, some formal calculi for several different situations, and just following formal rules to do these calculations without any regard to the underlying interpretation. Okay? And so in this way, he kind of, Boole anticipated some of the important parts of the modern axiomatic method. You know, the axiomatic method, though it started with Euclid or even before him with Aristotle, the modern method is quite different, which evolved around the turn of the 20th century. And Boole's work was some kind of a precursor to this modern method. But of course, we know that Boole's method was limited largely, or just limited to propositional reasoning, but, and we want to go much farther beyond that. So, and it was much later with the invention of quantifiers, with the development of quantifiers, that formal logic was in a stage that could be applied to general mathematics, not just propositional logic. So, this introduction of formal symbols for quantifiers in the universal quantifier, existential quantifier, it was done by several people. It's been credited independently to at least Frege, to Peano, to Peirce, as far as I know. Yeah, and logic was further refined by Russell and Whitehead, who wrote out very detailed formal development of foundations of mathematics, which is called, they develop logic from first principles. Yeah, and there's a 2-volume, 3-volume treatise called Principia Mathematica. So within a short space of time, mainly stimulated by Hilbert's foundational program. The logical language that you use that we use today in mathematics had been developed, and so what this language at its very simplest, you can just regard it as some kind of a convenient shorthand, you know, which augment the usual mathematical symbols that with new ones for the logical concepts. You know? So of course it seems odd nowadays to say write the sum of A and B. Instead we write something like this. You know? And then we write something like this instead of saying P and Q. You know? So this symbolism is not just on the surface. The actual consequences of having symbols for these notions, it runs much deeper. You know? So I mean, getting a very precise formal syntax is a very crucial step. And so once we have this, we can bring quite much deeper logical arguments into the purview of mechanical computation. You know, remember, we are doing mechanical computation. There is no intelligence here. It's just a machine. You know? So symbolism and very precise syntax, formal syntax is a very crucial step. You know? And it took some time to evolve in the history of mathematics. So, at various points in the development of mathematics, people have tried to base the foundations of their subject of mathematics with very simple, with very limited concepts. You know? So, for example, the Pythagoreans, they tried to base mathematics just on the rational numbers. Irrational numbers were unknown at that time. They tried to develop all of number theory from just rational numbers, and they were kind of shocked when they were shown that there are things like square root of 2, which are not rational at all. You know? So, and then there was all this development of infinitesimals in the work of Newton and Leibniz while developing the foundations of calculus. So this disturbed a lot of people in the way the concepts had been employed. Yeah. Similarly, there were things like complex numbers and there were non-Euclidean geometries, which kind of upset the kind of foundations which were there for the subject. You know? These were totally new entities. People didn't know how to kind of justify this. And similarly, later on, there was Cantor with his infinite sets, which once again threw all of foundations of mathematics in kind of a disarray. So foundational worries have appeared again and again. Yeah, it was just not Cantor. Before him, there was non-Euclidean geometries. There was these infinitesimals. There was even before that there are irrationals. People had to find ways to kind of reconcile this with the ideas of mathematics that they had. So as these new concepts keep coming up and people keep finding out some ad hoc ways of trying to justify them as mathematical concepts, Hilbert came out with a more, it's an ingenious program to give mathematics a reliable foundation. So he observed that in the past, problematic ideas like non-Euclidean geometry or complex numbers, they had been they've been given a foundation based on some other well-known, well-understood concepts. Yeah, but with infinite sets, this kind of a program didn't seem to work because it hardly seems feasible to justify infinite sets with on the basis of finite sets. So Hilbert proposed something different. So he said, don't focus on the mathematical structures themselves, but focus on the proofs. You know? And Hilbert said, once you have a suitable formal language, the mathematical proofs could themselves become an object of mathematical study. Okay? And this he called metamathematics. You know? So, I mean, if I'm sure there are lots of mathematics students in the audience, you see lots of theorems and proofs in books on mathematics, but they never tell you what is a proof. You know? If you want to find out what is a proof, you have to look at books on logic. So this is what uh, this is what I want to emphasize here. Yeah? So Hilbert was the first one who said concentrate on the proofs, yeah? and uh, and and study those proofs themselves as objects of mathematical study, just like you do groups or rings or topologies. Yeah? So our main object of study is a proof here. So, and Hilbert said that the hope was that once you have some controversial abstract concepts, you know, and you reach some concrete conclusions from them, then you may be able to show that these concepts are valid, or you may even be able to reach these conclusions even without those new concepts. So this was Hilbert's major idea. So, but then we know that Gödel came along, and there was a major blow to Hilbert's program. There are these famous incompleteness theorems which show that formal systems for deducing mathematics have their own essential weaknesses. Yeah? So, so Gödel showed that if you have a formal system of deduction which satisfies some very natural conditions, it turns out to be incomplete, in the sense that you can have something that you can write down very clearly, very formally, and it's a true statement, but nevertheless you'll never be able to prove it. Okay, so so it's generally agreed that Gödel's results came out and dealt a blow to Hilbert's program, as Hilbert had originally envisaged. But this is still something worth thinking about. So what is certainly true is that Gödel's theorem was was the first of a variety of impossibility results, which only become possible when the notion of a mathematical proof is formalized. So, so Gödel has written that he could not have come up with these results without having Principia Mathematica before him. Russell and Whitehead completely formalized the way mathematical proofs were written without any. So if you have time, I'm sure your libraries will have this book, Principia Mathematica. I don't recommend you to read them at all. Just go flip over and look at how the book is. It's just filled with symbols. He's trying to prove theorems completely in a symbolic way, and and the notion of proof is very, very well formalized in that. And Gödel says that without having recourse to Russell and Whitehead's work, he could not have come up with these results. So, so these impossibility results, kind of like Gödel's results, they become possible only when the notion of proof is mathematical proof is formalized. So after that, inspired by Gödel's incompleteness results, there is the work of Church and Turing. They proposed definitions of mechanical computability. And there is Hilbert's Einstein's problem, which is the decision problem for first order logic. This was again showed to be unsolvable according to the definitions that these people came up with. So and all this work, even though it looks like all negative results, this kind of showed the limits of mechanical calculation. But on the positive side, these Turing machines, which was an outcome of this line of work, they were an important inspiration for the development of computers. And before long, people began to investigate actually using computers to formalize mathematical proofs. So it's some kind of a strange turnaround in the history of foundations of mathematics. There were a lot of negative results, and one of the outcomes was computers, which is again now being used to formalize mathematical proofs. So, so in the background of all these incompleteness, undecipherability results, there are of course essential limits to what you can do with automated reasoning. So if you want a computer program to fully kind of mm, so which will automatically prove theorems. You just give it a theorem and it will prove it for you. So those things don't exist. You can clearly show impossibility results that if you have a machine of that sort, then you can end up solving the halting problem, okay, which is clearly unsolvable. So there are limits to what you can do with completely automated reasoning, with computer-aided proof, but nevertheless, there are interesting possibilities which have been explored. So, so at this point, I should mention that Gödel's results apply not just to computer programs; they also apply to human reasonings. So any kind of mathematics that you can formalize in from the axioms of Zermelo-Fraenkel set theory, in terms of sets, then you have all the limitations that Gödel has shown you, even if you are going to do mathematics with human beings and not with computers. You know? So if you start with any conventional set of mathematical axioms, there is, at least on the positive side, there is a semi-decision procedure that can in principle verify that what the theorem that you have is a logical consequence of these axioms. You know? So suppose somebody shows you a new theorem, we don't have an automated way of coming up with a proof of it or showing it as false. But at least there is a semi-decision procedure which you can verify that this is indeed a consequence of those axioms. If somebody gives you a proof, then you can verify it with a computer. Okay, and um, and then so there is Martin Davis's work, the first computer program for Pressburger's algorithm. You know? So, um, so this was the first computer theorem prover, so to speak, which could prove formulas which involve quantifiers or natural numbers and which had a linearity restriction ensuring decidability. So decidability is crucial to us. So that was some kind of a historical survey, which I stopped this historical development with the first computer program that came around for doing mathematical proofs, which is from Martin Davis. So, like I said, there are various communities in the computer science. Mm, Among computer scientists who have been using computers to deal with proofs. So there are people who use computer algebra systems, and then there are people who use theorem provers, and there is quite a distinct disconnect between these two communities. So let me show you some major aspects of these two kind of systems. So so both computer algebra systems and theorem provers, they are both computer programs which help people with some symbolic manipulations, with formal symbolic manipulations. But like I said just a while back, there is very little common ground between them. And the internal workings of the systems are completely different, and even the communities of people, implementers, the users also seem to be completely disjoint. So just here are some of the axes along which we can distinguish computer algebra systems and theorem provers. Um, there is a notion of logical expressiveness, about how clear the semantics is and how much logical rigor you have. And then, of course, these systems have their own weaknesses. So let me explore. Let me tell you a little bit more about these aspects. So what about expressiveness? So if you have a typical computer algebra system, like Maple, so they have a rather limited style of interaction. What do? You type out an expression, and then the computer algebra system thinks for a while, and then it returns to you another expression, E prime. Okay. The implication is that E is equal to E prime. And occasionally this can get slightly more sophisticated, where you have some additional side condition for this equality to be true. So, but what remains is that there is a simple equational style of interaction. This is the most usual with computer algebra systems. On the other hand, if you're looking at theorem provers, then they have a very sophisticated mathematical language, and they can write down things like this, like epsilon delta method for continuity. So you have, what we have is a full logical language with quantifiers, which unifies and also generalizes existing known concepts from various branches of mathematics. Okay? So this is a this so this is a major difference between computer algebra and theorem provers, where theorem provers have a more expressive language. So, for example, as an instance of, of generalizing and unifying various notions from mathematics, you can show that if you look at quantifier elimination in real closed fields, starting with Alfred Tarski's work, then you can show that it's a natural and a far-reaching generalization of what's called Sturm's algorithm for counting real roots of a polynomial. So these are work which emerged in totally different areas of mathematics, but surprisingly they seem to be have a very common starting point. So similarly, there are people have shown that quantifier elimination is another way of viewing the notion of projection in Euclidean space, and then there is Shirley's constructibility theorem in algebraic geometry, which again shows that we are just doing quantifier elimination in some other guys. Yeah. So, all right. So the next uh, dimension along which I want to distinguish computer algebra systems and theorem provers is the notion of semantics. So the underlying semantics of computer algebra systems is often unclear. Yeah? And though some of them may be more explicit, some of them are less explicit. But so, for example, if you are dealing with a polynomial expression like this, you can read it in different ways. You know, you can read it as a polynomial rings over reals or complex numbers. You know, or you can read it as an associated function which goes from R to R, or just as a value of the expression for some x which is a real number. So in the computer algebra system, it's not clear what is it that you are dealing with immediately. Okay, so similarly there is ambiguity over several complex functions such as square root, logarithm. You know, it's not really clear what sense the integral is. Is it a Riemann integral? It is a Lebesgue integral? Is it just an antiderivative? It's never clear. Yeah? So these kind of ambiguities, they sometimes it doesn't matter which interpretation is chosen. You know, but there are situations where this distinctions matter. If you're doing serious mathematics and doing some serious proofs, non-trivial stuff, these differences are very crucial. So in contrast, if you are looking at theorem provers, then they start with a very strict and precisely defined logical foundation, and they build up everything else, all other mathematical concepts, by a sequence of definitions starting from these very basic brick blocks. So HOL is the name of a theorem prover. It starts with very few basic axioms for higher order logic and some couple of notions from set theory, and these are all given a very precise semantics in the development of HOL. So from this foundation, everything else is built up. Natural numbers, lists, you know, real numbers, complex numbers, they are all built up without any new axioms. Mm. So the next dimension of difference is the notion of logical rigor. Even when a computer algebra system can be relied to give a result which admits a precise mathematical interpretation. So we've been talking about semantics just a little while back. So even if the interpretation is precise, that doesn't mean the answers it gives are always right. You know? So even you just have to believe me on this. If you take a computer algebra system, just a little bit of effort, it's not very hard to get incorrect answers out of it. You know? And so particularly there are simplifications which are troublesome, which involve complex branch cuts. You know? So if you're talking about simplifications like this, log of xy is log of x plus log y, this is fine most of the time, but if you're doing complex analysis, then you have to go into things like branch cuts. You know, things get more complicated. So let's not get into that now. You know? So in contrast, theorem provers take considerable care about all the theorems that are deduced. They deduce it in a rigorous way, and all conditions are made explicit. You know? So in fact, a system like HOL, it constructs a complete proof with a very simple basic kernel. So of course, you can always say that nothing is completely ever certain, but But if you have a theorem and a proof in this system, it's very likely to be correct. Unlike a computer algebra system. So what about, so all along I've told you um, ways in which theorem provers are better than computer algebra systems, but everything is not glossy about theorem provers. They have their own weaknesses. So let me point out a couple of flaws. Yeah. So it turns out that computer algebra systems are much easier to use. You don't need to be a programmer. You don't need background in logic, in foundations of mathematics, to be able to start using it. You can just switch it on and just start playing with it, and you can use these systems. But these theorem provers are much harder to start to get used to. And computer algebra systems, they implement many algorithms which are useful for solving concrete problems. For example, like factoring polynomials, finding integrals. And in contrast, theorem provers focus just on proof search and logical systems. And and if you want to express any high-level mathematics, it's often non-trivial to do it in with the current state of technology. Of course, all this will change in the coming years. So so it's not surprising that computer algebra systems are more or less mainstream tools in various fields, whereas theorem provers has been still confined mainly to logicians and computer scientists who are interested in formal correctness proofs. So it, like, the strengths and weaknesses of these two systems seem perfectly complementary, and it seems a natural good idea to kind of put them together and get the best of both worlds. So one promising idea is to use the CAS as an oracle. So you come up with a conjecture which in mathematics, and you want to be able to prove it or disprove it. So what do? First, use the computer algebra system as some kind of an oracle. It will test it out for you. Suppose you have a conjecture in number theory. Okay, this computer algebra system will explicitly check it out for till very large numbers, and then say, I don't find any contradiction to it. Okay, then you can set out using a theorem prover to start to prove it. Okay, so you treat it as some kind of a guessing machine for your work, the computer algebra system, but but um, but the actual proof has to go through a theorem prover. Okay, of course, this line of work, this works only for problems where checking a result is much easier than deriving it. And of course, there are several exceptions to this, like we have seen in the morning today already. So factoring, so there are, okay. So what about research in automated reasoning? So people have been going in various ways. So here are some of the major directions in which this field is being explored. There is the AI versus the logic-oriented approach to this. And then there is the automated and interactive, and then there is the proof search versus special algorithms approach. So let me tell you briefly about these various ways in which people are exploring these areas. So some of the people have tried to look at automated theorem proving by trying to emulate the way humans reason. So you look at how do human beings work, how do they prove theorems, and try to do the same thing with a machine. Okay? So you can call this the AI approach. So right in 1950s, there was Newell and Simon who developed a system that could prove many of the simple theorems in Principia Mathematica, automatically. Okay, and then there was somebody else, Galanter, who did similar things for Euclidean geometry, using human-style diagrams to direct or to restrict proofs. So basically, they are trying to mimic with a machine the way humans work. On the other hand, a completely different approach was taken by Martin Davis and his collaborators. They they tried to implement proof search algorithms using results from logic, from what is called Genson's cut-free sequent calculus, this is completely remote from the way humans prove theorems. You know? So they tried to implement this with a machine, and the early indications are that these machine-oriented methods perform much better than the techniques that I showed you earlier, which try to mimic human intelligence with a machine. Okay. So here is something from Nelson Wong. He was a collaborator of Godel, and he talks about a simple systematic program for a fragment of first order logic with these quantifiers all there exist. You know, so he says that there is a fundamental inadequacy in the approach of Newell, Shore, and Simon, which try to mimic uh, humans with a computer. You know? He says you don't need to kill a chicken with a butcher's knife, and Nelson Wang's impression is that um, this work of Newell and Simon fails even to do that. So so with the success of Martin Davis's work, over the next few years, decades, far more attention was paid to systematic machine-oriented algorithms to do proofs. You know? And Larry Voss was one of the most successful practitioners. He attributes this success to the fact that they try to play to a computer's strengths instead of trying to emulate human thought. Okay? And still today, there is still a lot of people who doing research on the machine-oriented side, but there have also been notable results, successes with people from those who have tried to mimic human-oriented approaches. You know, so there is something from Bledsoe. He tried to formalize methods often used by humans for proving theorems and analysis, and um, and uh, and Bledsoe's student uh, Boyer, along with Moore, they developed a remarkable theorem prover called Enquetum, which this is again just a name of a theorem prover, which can perform automatic generalization of arithmetic theorems and prove theorems by induction. You know? So the success of Boyer and Moore's system, it led Alan Bundy to come up uh, with with a system which has a simple conceptual framework, which he calls a system of reasoning based on proof planning. You know, so depending on the point of view that you have, and you can look at. I mean, there has been considerable interest in both approaches to doing theorem proving, both the human approach with computers or a completely machine-oriented style. So, and then the other dimension to look at is automated versus interactive. You know, so there are things where you leave it completely, leave the system completely alone, you know, to prove your theorem for you. Just a little while back, I said that it's an undecidable problem. But if you restrict your domain in which you want to do proofs, then it can succeed. And there was a famous long-standing outstanding problem called Robin's conjecture, which concerned the axiomatization of Boolean algebra. This was completely solved with a machine, you know, with a theorem prover, an automated theorem prover called EQP. Okay, so this is just one of the results that I quote. There have been several other things to their credit. So, but if you look at this carefully, it seems that at present neither of these approaches by themselves, neither a systematic algorithmic approach or a heuristic human-oriented approach, can kind of prove a wide range of difficult mathematical theorems automatically. So, besides, there is also a conceptual objection you can come up with at this point of time. It's hardly desirable to automate proofs that humans are incapable of developing themselves. Yeah. So, so, see, here is something from Dijkstra, who's done a lot of work in computer science. He says, I consider mathematical proofs as a reflection of my understanding. And understanding is something we cannot delegate. either to another person or to a machine. Yeah. So this runs completely counter to the whole area of trying to doing proofs automatically. Um, so, so what we can do is look at keeping in mind Dijkstra's views. Um, we have a more easily attained goal in the sense that where you create a system which can verify a proof that's done by a human. Yeah. So proofs, we are saying that it's something for us to do as a vehicle of our understanding mathematics, but you can use a machine to check that the proof is correct. Yeah. So the machine just acts like a clerical assistant, which tries to point out uh, human errors such as implicit assumptions that you make or forgotten special cases. Yeah. So, and at best, the computer may process by automating certain part of the proofs. Yeah. So, because all proofs often contain parts which are just routine verifications or which are just amenable to automation such as algebraic identities. So those parts which are routine, you can leave it to the machine. The rest you develop with a human being, and the computer just checks that you have not made any errors, mistakes in doing the proof. Okay, so this is where interactive proof checking comes in. Yeah, so this is again from Nelson Wang. So we have what we have in this interactive way is to have a human and a machine working together to prove theorems. Yeah, so mm, so okay, let's go ahead. So, okay, so there we have the idea of a proof assistant. You have a machine which is just some kind of a clerical assistant to a human being. So this started attracting attention in the late 1960s, and now there are several proof assistants available um, for use. You know. The early proof assistants were based on a batch model, just like programming was going through a batch model of programming. So you submit the entire program to the computer, and then it will compile it for you. You know. So nowadays you have more interactive way of writing down programs. So this initial work on proof assistants worked on a batch model. You know. But and even with that, there was and then slowly theorem provers became more interactive, yeah, which was initially called semi-automated mathematics. So, mm, all right, let me skip this. Um, and with this semi-automated mathematics, the first successes came around what is called Sam's lemma now. So there was a unproven conjecture in lattice theory, which came to be proved with the advent of interactive theorem provers. Yeah, and after that, several other major theorem proof assistants appeared: Automath, Mizar, LCF. All these are still around today, and there are people actively working on developing these systems mm, even now. And there are several other theorem provers which have evolved from these. You know, I'm giving you these names so that you can look them up and to see whether it's of interest to you. Yeah? So all these are like completely different programming languages, you know, for writing down proofs. So some of them may appeal to you, some of them may not. Yeah? So you may like Java, you may not like Prolog. So it's something like that. Yeah? So there are various ways in which people have come up to write down formalized proofs, and you can see which one is to your taste. Yeah. So people are doing both. There is research work in both interactive as well as automated theorem provers, and and there are even annual competitions which try to hold competitions on test problems to see whose system has succeeds better. Yeah. Um, okay, and all right, let me skip this in the interest of time. Let's look at applications of interactive theorem proving. There are two main applications. Yeah? One is to verify the correct behavior of computer systems. Computer systems are made up of several things. There is hardware, there are protocols, there is software, and there are combinations of them. So how do you really know that you have a sorting algorithm? How do you know that it does always its job properly? Yeah, and then how do you know that if you have a server which works under certain protocols, it will always respond to a request? Yeah? So there are various issues like this which you can try to formally establish using theorem proving. So so if you write programs in typical programming practice, you write programs with very clear logical ideas behind them. Yeah? But the final properties that are claimed, they are based on just intuitive understanding together with a variety of inputs which are used for testing. Yeah? So um, So if you have done any serious programming, then you know that it's quite difficult to write a program that always performs its intended function. Yeah? And and these we call bugs, where there are several situations where programs don't behave as we intend them to. Yeah? And so testing is completely inadequate. If somebody sells you a new product, a new software, or some computer system, and you want to certify that this indeed will work properly, of course you can test it out for some sample inputs, but that doesn't guarantee anything. Yeah? It works for those inputs. That's all you can say. This is not. So what we want is something like a proof of a mathematical theorem. Yeah? You don't have a conjecture and say this succeeds in a few instances. Otherwise, I don't know whether it is true or not. Yeah? So we want computer software, computer systems to be completely reliable, and uh, and that was the whole idea of formal verification. And this notion of interactive theorem provers come in very handy to do that. Yeah? So okay. So let me skip over this and look at the other application. The other application is a formalization of mathematics itself. You know? So here is from Bourbaki. He says the correctness of a mathematical text is verified by comparing it more or less explicitly with the rules of a formalized language. You know? And this is what we know, the notion of a mathematical proof. This is the final arbiter of correctness in mathematics, and this is what is of interest to us. Yeah? So, so here is something from Saunders Maclean. Again, he says when a proof is in doubt, its repair is just a partial approximation to the fully formal version. Yeah? So you do proofs in a more informal language, but wherever there are some kind of ambiguities, some doubts, then you go down to its more formal version of it. Yeah. So um, with now that we have computers, there is actually the possibility of actually formalizing mathematics and its proofs. At the time that Russell and Whitehead wrote Principia Mathematica, the results were quite elementary. They does not even cover classical real analysis. Forget about doing mathematics at a research level. Yeah? So, but now we are at a stage where we can actually do really state-of-the-art mathematics. So, um, so apart from just, you can just treat it as some kind of intellectual hobby or something, but it's not so. So there is a real increase in reliability. So for example, if you look at mathematical proofs, they are subjected to peer review before publication. But there are plenty of well-documented cases where results have turned out to be faulty later on. Yeah? So a notable example was the first early proof of four-color theorem. Yeah? And there was a flaw which was noticed only about 10 years later. Yeah? And then of course somebody came up with corrected the proof. Yeah? And so it was conclusively proved only much later. Yeah? So these are the kind of things that we hope to be able to eliminate with interactive proof assistance. If I have proof and if the computer verifies it, I can detect errors in it much earlier. So here is something from Littlewood, who was Hardy's collaborator. So he says that when he wrote a paper for Annals of Mathematics, in formulating a proof, a plus sign got omitted. It became a multiplication sign. and the resulting false formula got accepted as a basis for some ensuing fallacious argument. So I'm not talking about a beginning student in mathematics. There are very well established mathematicians, leading figures at the time in mathematics in their time, and they still make errors in proofs. So here is something interesting. There is a book by Lecat. Unfortunately, it's in French. This was written about 70 years ago, and he makes about 130 pages of errors made by major mathematicians up to the year 1900. So with the kind of number of theorems which are being published today, with people who are not even trained mathematicians, so if you do a project like Lecat, you need a whole journal for itself. So, so moreover, many proofs like the proof of the Kepler conjecture, the four-color theorem, they also rely on something different. They rely on extensive computer checking. There are several cases that have to be checked, and it's not clear how to bring them within the traditional process of peer review. There's a lot of calculations, computations to be actually checked in the proofs. So at present we are still far from the stage where somebody can just pick up one of these theorem provers and start to formalize their own work. But things are getting better. More and more formalized mathematics is being built up into substantial libraries which can be invoked directly from the system that you're using, and quite a few substantial results have been formalized by now, and this list is growing. I just put out a few names here. So as mathematical libraries are built up more and more, these interactive systems will become more powerful and user friendly, and we can expect to see more mathematicians using them rather than just computer scientists or logicians. So that brings me to the conclusion of my talk. So automated reasoning is already finding applications in formal verification and formalization of mathematical proofs. At present, applications to mainstream applied mathematics seems to be limited, but theorem proven has been applied in some unexpected ways. Like for example, there are several combinatorial problems which are better solved by translating them to SAT than with customized algorithms. So, right, writing mathematics in a way that a computer can understand is still a very labor-intensive operation. So somebody has made an estimate. If you take a typical graduate text in mathematics and look at proofs in that and try to translate them in a way the computer will understand, it takes almost 2 hours per source line of it. Okay, so you need to reduce this time with the development of with libraries, better languages, and in fact all the experience that we have with developing large software. So the main goal of interactive theorem proving is to reduce the cost of formalization, cost in terms of time and energy that is spent in formalizing, and improve the benefit of it. So, um, so let me conclude with the quote from De Bruijn, one of the pioneers in this area. He says, if you can't explain your mathematics to a machine, it's an illusion to think that you can explain it to a student. Okay. So I stopped with this. Um, my thanks to the organizers of ASCAT to give me an opportunity to come here, and thanks to all of you for listening. Yeah. Um, okay. So here are a couple of volumes that I edited, which has a collection of papers with various applications. You can look at them. Yeah. And if you want more recent work, send me an email. I can give you papers from with my students. So one of my students went to the Bombay Stock Exchange and looked at the algorithms that they use and tried to show correctness proofs of them. You just take them on their word, the way trading is done. How do you know that they have them not actually deluding themselves by using wrong programs? Okay. So, all right. Thank you. So if you have any comments or criticisms, I'm open to it.
Thank you, Professor Raja. Now it's time for questions. I hope we will have some questions to ask him. It was a very interesting talk. Yes.
So, just from our perspective, Silaromara perspective,
Yeah.
what do you think that your automated theorem proving techniques, how can they help
Yeah.
in the field of cellular automata?
So one direct method I can see is if you have really complex theorems results in cellular automata, then you can try to 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 put them in this format, to see to actually verify their correctness. Okay.
So for the correctness only,
Yeah.
for the correctness of theorem.
Yeah, for the correctness. Yeah, that's an immediate application. That one way you can try to use these as tools for for proving substantially complex results in CA. Using these.
Okay.
That's one. The other is to go into the technology of this and see whether CA itself will help in the implementation of these systems better. That will take much more effort.
Yeah, right.
There are still a number of ways in which these systems. I mean, there's a lot of scope for improving them, and you don't know what kind of ideas come in handy to actually see to make them function better. Maybe ideas from CA help. I don't know.
Okay. Do you think it's possible that your system will be developed, implemented by cellular automata?
Maybe, yeah. I don't rule out the possibility.
Okay.
Surely.
Thank you.
So there's this recent lot of publicity about lean
Yeah.
and mathematicians using famous mathematicians have been using these
Yeah. Right.
things. So
So
is,
lean.
is,
Yeah. Go on.
is something new happening, and I mean, why they're finding it so interesting? Or, I mean, automated theorem proving has been around for a long time, but
Yeah. So some of this is the limit of some fields medalists have got interested in this.
right.
So that this lean is an outcome of that. Yeah. And so
But is there
Microsoft
something?
is interested now in that. Yeah. So they're trying to develop systems that people with community will hopefully increase. That's the idea. Okay. So lean is just another theorem prover, just like the Bayer mode, just like Koch. There are several of them. Yeah. So there is nothing that I can particularly ascribe to lean to distinguish it in any way. Yeah. So there are about 15 or 16 theorem provers, proof assistants that are available, and lean is one of them. And the community of lean seems to be growing because of these prominent mathematicians who have shown interest in it. Yeah. Timothy Goers, and there are some people who.
Yeah. So I mean, I'm wondering, does these mathematicians
Yeah.
just hit up
Yeah.
chance upon lean and
Yeah.
they're riding the bandwagon, or is there something?
No, so they've
Specific?
started using it for their work, at least.
Yeah, but
Yeah.
why not Cock, or why not, or whatever it's renamed version, or
Yes.
why not HOL?
Maybe they find lean to be easier to use. Yeah. It's been so
Hmm.
people have designed it who are basically who have been working on developing software for a long time. They probably have different insights into structuring the language, just like language design, just like programming language design. This is a programming language for writing down proofs. So lean is better in some ways. Definitely, I'm not taking away credit from lean, yeah, but but still, I would say it's still not substantially very different from other theorem provers. Yeah, maybe to get started, lean may be easier, but you'll reach a learning curve, stumbling block sometime in say in a few months. Yeah. Okay.
Sir, I have one doubt. Actually, I didn't understand one thing.
Mm.
Yeah. So you were saying that uh, almost not to go for automated theorem proving, rather to go for the interactive theorem proving.
Yeah.
So automated means where there was some role of AI that I understood, that you are suggesting to avoid.
No,
Is
so
that
automated, I meant that you leave the machine completely alone. You come up with a conjecture and you give it to the machine as input, and the machine gives you output the proof of it. You know? So that in the most general case cannot be done. You can show an impossibility result, but if you confine yourself to very specialized, very particular areas, of mathematics, say, then it can be done. Okay. So that what the computer does can be either mimicking the way a human works. So that's what I call the AI approach.
okay?
I mean, somebody has to build the machine. That's part of this field. Somebody has to build the system right on the prover, which actually comes up with the proof. So the internal workings of the prover could be in a way that it's kind of trying to mimic a way a human being works. So those things have not been very successful. They succeeded in a few places, but but the approaches which seem to rely on a totally different way, completely on the way proof is done in logic, there seems to be working better, at least now. Now things may change with evolve as we get more insight, as more things come, the position may change, but right now the AI approach doesn't seem to be doing well.
So, do you think we can get some new proofs by using this computer-aided theorem proving?
Yeah, surely. Yeah. So new proofs are there all along when you're doing software, trying to prove correctness of, say, of protocols, of computer systems. So these are in effect new theorems, so to speak. Yeah. This is not group theory. This is not topology, but this is a formal area where you need correctness of, I mean, proof as we know it. Yeah. So there have been some. So there are several results in that. But if you look at classical mathematics, then those numbers are much fewer. Yeah? Okay, where the proof is fully automated, where you don't know how to, where you didn't have a proof before. Okay, but but there are several long proofs in mathematics, like the four-color theorem, which people had a proof, but nevertheless, now you have a completely formally checked proof for this, with these systems.
Thank you for the nice talk.
Okay.
I'll hand over to.
Thank you, sir. I would now request Dr. Mamul Bakas, sir, to kindly present a token of appreciation to our eminent speaker. Thank you, sir. We'll now take a short tea break till 3